Picture this. No steam engines, no steel beams, no calculators, no CAD software. Just human hands, ropes, stone, water, and an almost impossible amount of patience. And yet thousands of years before the first factory chimney ever smoked, human beings were already building sewer systems that flushed waste out of cities, aqueducts that carried water across entire mountain ranges, and stone structures so precisely fitted together, you still can't slide a credit card between the blocks today. We tend to think of the Industrial Revolution as the moment engineering was invented. Gears, machines, mass production. That's when humans supposedly got clever. But that story leaves out some of the most brilliant problem solvers in history. This is part one of a trilogy exploring the forgotten builders who mastered real, functioning engineering centuries before smokestacks ever existed. Today we're starting with three ancient civilizations that turned precision into an art form: Rome, Egypt, and the Indus Valley. Grab a drink, get comfortable, settle in. This one's going to be a long, detailed ride. And let's go meet the original engineers. Let's start somewhere familiar, but with a twist you might not know. Everyone's heard of Roman aqueducts, but the real genius wasn't just building a stone bridge that carried water. It was the sheer precision behind it. Rome's first aqueduct, the Aqua Appia, was built in 312 BCE by the censor Appius Claudius Caecus, the same official who commissioned the Appian Way. It ran almost entirely underground for about 16 kilometers, since early Roman engineers hadn't yet perfected the tall, arched bridges we picture today. Over the following 5 centuries, Rome built 10 more major aqueducts, including the Aqua Marcia, the Aqua Claudia, and the Anio Novus, eventually forming a network of roughly 500 kilometers of channels. Though only about 50 kilometers of that ran above ground on the famous arcades, with the rest tunneled underground to protect the water and maintain the gentle gradient needed for consistent flow. That gradient is the real feat. Aqueducts needed a slope steep enough for water to flow, but gentle enough not to erode the channel or overflow at speed. Often just a few centimeters of drop per kilometer, sustained across dozens of miles of hills, valleys, and uneven ground. Roman surveyors achieved this using an instrument called the chorobates, a long wooden plank fitted with a water-filled groove that worked like a giant spirit level, alongside a sighting tool called the dioptra for measuring angles across distance. We actually have a detailed first-hand account of how seriously Rome took its water supply. Around 97 CE, a Roman official named Sextus Julius Frontinus was appointed Curator Aquarum, the official in charge of the city's water system, and he wrote a treatise called De Aqua Eductu, cataloging each aqueduct's length, capacity, and condition, and even exposing widespread water theft by unauthorized taps along the system. Proof that Rome's engineering bureaucracy was as sophisticated as its stonework. Then there's Roman concrete, arguably one of the most underrated materials in history. Engineers mixed volcanic ash, called pozzolana, named after the town of Pozzuoli, lime, and seawater to create a concrete that didn't just survive underwater, it actually got stronger over time as seawater reacted with volcanic minerals inside it, forming a rare mineral called aluminum tobermorite that continued crystallizing for centuries. Modern researchers studying harbor structures at sites like Caesarea and Baiae found this self-healing reaction still active 2,000 years later. We're still trying to fully reverse engineer the exact formula. This same concrete let Roman engineers build the Pantheon's dome around 126 CE under Emperor Hadrian, still the largest unreinforced concrete dome on Earth, with a design that graded the concrete mixture itself. Heavier aggregate like basalt near the base, lighter volcanic pumice near the top to reduce structural stress as it rose. Rome's engineering genius went well beyond water and domes, too. Beneath the city itself ran the Cloaca Maxima, one of the world's earliest large-scale sewer systems, originally built as an open drainage canal around the 6th century BCE under the semi-legendary king Tarquinius Priscus, later covered over and expanded, which drained the marshy Forum Valley and carried waste into the Tiber River. Parts of it are still functioning as storm drainage in Rome today, nearly 2,600 years later. Roman bathhouses relied on the hypocaust, an underfloor heating system where wood-fired furnaces called praefurnia pushed hot air through hollow spaces beneath raised floors, supported on small pillars called pila, and through hollow flue tiles inside the walls, effectively inventing central heating well over 1,000 years before it reappeared in Europe. The baths of Caracalla, completed around 216 CE, used this system at a massive scale to heat pools for an estimated 6,000 to 8,000 daily visitors. And at the Colosseum, completed in 80 CE, engineers built a velarium, a retractable canvas awning system rigged through masts and rope pulleys, operated by a dedicated crew of sailors from the Roman Navy that could be extended to shade roughly 50,000 spectators from the sun. Beneath the arena floor sat the hypogeum, a 2-level underground network of tunnels, cages, and at least 24 vertical lift shafts using a counterweight and pulley system to hoist animals and scenery up through trapdoors into the arena in a matter of seconds. The seating design itself was engineered for crowd flow, with numbered entrances called vomitoria, allowing the entire stadium to empty in under 15 minutes, a design principle still used in modern stadium engineering. The Romans also built over 400,000 kilometers of roads across the empire, constructed in careful layers, a foundation layer called the statumen, made of large stones, then the rudus, a layer of smaller rubble mixed with lime, then the nucleus, a compacted gravel and sand base, and finally the summa crusta, tightly fitted paving stones on top, engineered with a slight camber so rain would drain to the sides instead of pooling. Their arch and keystone bridge designs, seen at structures like the Alcantara Bridge in Spain, built under Emperor Trajan around 106 CE, distributed weight so effectively through compression that some Roman bridges are still carrying vehicle traffic today, nearly 2,000 years after construction. Alongside the roads ran the cursus publicus, a state-run relay system of rest stations and stables spaced roughly a day's travel apart, letting messages and officials move across the empire at a pace not matched again in Europe until the arrival of railways. Where valleys were too deep for standard arched bridges, Roman engineers used inverted siphons, sealed lead or stone pipes that carried water steeply downhill into a valley and back up the other side, relying on the simple principle that water seeks its own level. The siphon at Aspendos in modern Turkey and the one serving Lyon in ancient Gaul crossed valleys using pressure alone, a solution requiring precise calculations of water pressure that Roman engineers arrived at largely through empirical testing rather than formal fluid mechanics. Rome's harbor engineering deserves its own mention. At Portus, the port built to serve the capital under Emperor Claudius and later expanded by Trajan, engineers constructed massive breakwaters using concrete poured into wooden forms and lowered into the sea, some incorporating hollow clay amphora inside the concrete mix to reduce weight without sacrificing strength, an ancient version of the lightweight aggregate techniques still used in engineering today. Maintaining all of this took a dedicated workforce. Frontinus's writings tell us Rome employed a standing crew called the Familia Aquaria, several hundred trained slaves and freedmen responsible for round-the-clock inspection and repair of the aqueduct network, along with a standardized system of lead pipe sizes called the quinaria, used to regulate exactly how much water any household or public fountain was legally entitled to draw. An early form of water rights metering. For laying out straight roads and perfect right angles for city grids and forts, Roman surveyors used a simple cross-shaped tool called a groma, which used hanging plumb lines to sight straight lines across long distances, letting military engineers lay out an entire legionary fort's grid in a matter of hours. And when Emperor Trajan wanted to commemorate his Dacian military campaigns in 113 CE, his engineers built Trajan's Column, a 30-meter marble monument wrapped in a continuous spiral relief carving 190 meters long, requiring builders to hoist and precisely stack drum-shaped marble blocks while leaving a hidden internal spiral staircase carved through the center. A combined feat of structural engineering and stone carving logistics. Now let's go back even further, to Egypt around 2560 BCE, to the Great Pyramid of Giza. Built for the pharaoh Khufu, this pyramid contains an estimated 2.3 million blocks of stone, some weighing as much as 80 tons, and it was completed with an accuracy that borders on unbelievable. Its base is leveled to within just a couple of centimeters across a footprint of over 5 hectares, and its sides are aligned to true north with an error of only about 1/15 of a degree. How did they do it without cranes, iron tools, or the wheel for heavy hauling? Archaeologists have found real evidence, not guesswork. Wooden sledges dragged over paths wetted with water to reduce friction, a technique actually depicted in Egyptian tomb paintings, and later confirmed through physics experiments showing wet sand reduces dragging resistance significantly. Along with ramps, levers, and worker villages near the pyramid site containing bakeries, breweries, and medical facilities, showing evidence of healed bone fractures that indicate injured laborers were cared for and allowed to recover rather than being discarded. This is strong physical proof these were paid, organized laborers, not slaves as popular myth long suggested. Papyrus logs discovered at the Red Sea port of Wadi al-Jarf dated to Khufu's reign and considered the oldest inscribed papyri ever found, even describe an official named Merer, who led a team of about 40 men hauling limestone blocks by boat down the Nile from the Tura quarries to the construction site, giving us a real, dated, first-hand account of the logistics involved. Inside the pyramid, engineers solved a serious structural problem above the king's chamber. The immense weight of stone above it risked collapsing the room, so they built a series of 5 stacked, relieving chambers, using massive granite beams to redirect the weight outward to the pyramid's sides instead of straight down. The grand gallery leading up to the chamber uses a core-belled ceiling, where each course of stone steps slightly inward as it rises, a technique that lets a passage narrow gradually to support weight without needing a true arch. Giza wasn't the starting point either, and Egyptian engineering itself was a story of trial, error, and correction. A century earlier, around 2670 BCE, the architect and physician Imhotep designed the step pyramid of Djoser at Saqqara, widely considered the world's earliest large-scale cut-stone monument, built by stacking 6 progressively smaller stone platforms. It represented a massive leap from mud brick construction, and Imhotep himself was later deified by the Egyptians for his engineering brilliance, one of the few commoners in Egyptian history to receive that honor. A few decades after that, Pharaoh Sneferu's engineers attempted the first true smooth-sided pyramid at Meidum, and it partially collapsed, likely due to an overly steep angle and unstable foundation, with the outer casing sliding off in a landslide of rubble still visible today. Undeterred, Sneferu's team tried again at Dashur, but midway through construction they noticed dangerous cracking and abruptly changed the angle partway up from 54 to 43 degrees, creating the oddly shaped bent pyramid, a rare, visible record of ancient engineers correcting a live structural mistake in real time. Their next attempt, the Red Pyramid, got the angle right from the start and became the first successful true smooth-sided pyramid, paving the way for Khufu's Great Pyramid a generation later. Egyptian engineers were equally skilled with water. Along the Nile, they built an extensive network of irrigation basins, using earthen dikes to trap floodwater during the annual inundation, then releasing it gradually onto fields to maximize fertile silt deposits before the growing season. A system refined over centuries that supported one of the ancient world's most reliable food supplies. To track the Nile's flood levels and predict harvests, they built nilometers, stone structures with marked columns or stepped shafts descending into the riverbed, allowing officials to measure the flood's height and estimate tax revenue for the year, since a poor flood meant a poor harvest. And at Karnak, the great hypostyle hall's 134 massive stone columns, some over 21 meters tall and nearly 3.6 meters in diameter, were raised and precisely aligned using earthen construction ramps that were built up around the site and then dismantled as the structure rose. A technique still debated and studied by modern engineers trying to reconstruct exactly how such heavy, tall stonework was safely maneuvered into place. Egyptian engineers also extracted single-block obelisks weighing over 500 tons using nothing but stone-pounding tools called dolerite balls to slowly wear away the surrounding rock. The unfinished obelisk still lying in the Aswan quarry today, abandoned after a crack appeared during extraction, gives us a rare, unfinished snapshot of exactly how the process worked. The Great Pyramid's builders didn't work in isolation from the rest of society either. Excavations at the nearby workers' settlement known as Hayt el Ghurab uncovered evidence of large-scale communal feeding operations, including cattle and sheep bones, suggesting workers were fed substantial rations of meat, alongside barracks-style housing organized in a way that mirrors military logistics more than forced labor camps. Further south, at Deir el-Medina, the village built for the artisans who carved the tombs of the Valley of the Kings centuries later left behind an extraordinary written record. Thousands of inscribed pottery shards called ostraca documenting worker attendance, wages paid in grain, medical leave, and even a recorded strike around 1157 BCE under Ramesses III, when wages were paid late, believed to be history's earliest documented labor strike. Egyptian engineers also tackled large-scale water management beyond the Nile's floodplain. Under Pharaoh Amenemhat III, around 1800 BCE, engineers expanded a natural depression in the Fayum region into Lake Moeris, using canals and a regulated channel connecting it to the Nile to store excess floodwater and later release it during dry periods, effectively creating one of the ancient world's earliest large-scale reservoir systems. A project so significant that Greek and Roman visitors centuries later still wrote about it with astonishment. Right beside the Giza pyramid sits the Great Sphinx, carved not from separately quarried blocks, but directly out of a single limestone bedrock outcrop left over from the pyramid quarrying process, meaning its builders had to sculpt downward and outward into solid rock rather than assembling it piece by piece, working around natural bands of harder and softer stone that still cause uneven weathering patterns visible today. Nearby in 1954, archaeologists uncovered the Khufu ship, a full-sized cedar solar bark over 43 meters long, buried in a sealed pit beside the pyramid in more than 1,200 individual pieces and later reassembled to reveal a hull. Built using a sewn plank technique, planks stitched together with rope through carved grooves rather than nails, showing Egyptian shipbuilders had mastered flexible, watertight hull construction that could still float when reassembled and tested millennia later. Here's one that rarely gets the credit it deserves. Around 2500 BCE in what's now Pakistan and northwest India, the Indus Valley civilization built cities like Mohenjo-Daro and Harappa with something most ancient cities didn't have: a fully planned citywide sewage system. Homes had private bathrooms connected to covered brick drains running beneath the streets, carrying wastewater out of the city, complete with sedimentation tanks along the route to let solid waste settle out before the water continued onward, and manholes for cleaning and maintenance. Streets followed a careful grid pattern running in straight north-south and east-west lines, suggesting real centralized urban planning rather than organic sprawl. Bricks across the civilization followed a standardized ratio of 4 to 2 to 1 by length, width, and height, meaning builders hundreds of kilometers apart were using the same measurement system, a level of standardization unmatched in the region for a very long time. Archaeologists have also found a remarkably consistent system of cubical stone weights across Indus sites, following a binary-like doubling scale, suggesting standardized trade, taxation, and possibly even shared regulatory oversight across the entire civilization, despite no evidence yet found of a centralized king or palace enforcing it. The Great Bath of Mohenjo-Daro is another standout, a watertight public pool roughly 12 meters long and 2.4 meters deep, built with tightly fitted, finely made bricks set in gypsum mortar and sealed with a layer of natural bitumen as a waterproof lining, predating Roman bathhouses by well over 1,000 years. Nearby, the city's massive brick granaries suggest organized, large-scale grain storage and redistribution, hinting at a coordinated food economy even without direct evidence of centralized rulers. At the site of Lothal in modern Gujarat, archaeologists uncovered what many consider one of the world's earliest known dockyards, dated to around 2400 BCE. It included a large trapezoidal basin connected to a river channel, engineered with an inlet and outlet designed specifically to manage the region's significant tidal range, letting boats enter during high tide and remain safely afloat even as water levels dropped, a level of tidal engineering not clearly replicated elsewhere in the ancient world for a very long time. At Dholavira, another major Indus site, archaeologists found one of the ancient world's most sophisticated water conservation systems, a network of at least 16 stepped reservoirs, some cut directly into bedrock, designed to capture and store seasonal monsoon rainfall for year-round use in an otherwise arid, water-scarce region. Some of these reservoirs were massive enough to hold millions of liters, and the entire city's layout, including channels and embankments, was arranged specifically to funnel rainwater toward them. The Indus Valley's engineering also supported a serious long-distance trade economy. Carnelian beads, seals, and ivory from Indus cities have turned up as far away as Mesopotamia, and cuneiform tablets from Sumer refer to trade contact with a distant land called Meluha, widely believed to be the Indus Valley civilization itself, meaning the same builders who engineered these cities' drains were also running a functioning maritime and overland trade network stretching over 1,000 kilometers. Indus seals, carved from soft stone and stamped with animal motifs like the famous unicorn bull alongside short inscriptions in the still undeciphered Indus script, were likely used to mark ownership on traded goods, suggesting formal commercial record-keeping even without a decoded writing system. Harappa and Mohenjo-Daro were also built with defensible elevated citadel mounds separate from the lower residential town, constructed on massive mud brick platforms that lifted the most important civic and religious buildings above flood risk, a form of proactive flood engineering in a region regularly reshaped by the Indus River's shifting course. At Kalibangan, another major site in modern Rajasthan, archaeologists uncovered a series of fire altars and evidence of deep, carefully lined wells, suggesting both ritual and practical water engineering coexisted at the city level. And in 2014, the discovery of Rakhigarhi, now considered possibly the largest Indus Valley site yet found, revealed the same standardized brick ratios, drainage principles, and civic planning replicated hundreds of kilometers from Mohenjo-Daro, reinforcing just how consistently this civilization's engineering knowledge spread across an enormous territory without, as far as we can tell, any centralized monarchy enforcing it by decree. This civilization left no monumental palaces, no grand tombs, no boastful pharaohs or triumphal inscriptions behind. Just quietly excellent, remarkably consistent infrastructure across a territory larger than ancient Egypt and Mesopotamia combined, which might be exactly why it's one of the most overlooked engineering cultures in history. And even its decline tells an engineering story. Sediment and paleoclimate studies increasingly point to the gradual drying up of the Ghaggar-Hakra river system, likely tied to shifting monsoon patterns around 1900 BCE. As that river system faded, cities dependent on its water and the trade routes running along it were gradually abandoned, and populations dispersed eastward toward the Ganges plain. A reminder that even the most disciplined engineering can't outlast a changing climate forever. That's part one. Rome's gravity-fed water empire and underground heating systems, Egypt's iterative trial-and-error mastery of stone, and the Indus Valley's quiet brilliance in sanitation and water storage. In part two, we're heading to sub-Saharan Africa, the jungles of Cambodia, and high into the Andes to meet builders who mastered stone without mortar and cities without wheels. Thanks so much for watching. If you enjoyed this one, leave a like and subscribe so you don't miss part two. See you there.